All right. We are looking at now, there we go, Introduction to Rate Laws. This one's a biggie, but it's a goodie, and it's a very important concept in this Unit 5. So rate laws, there's two different types, differential and integrated. The differential show the relationship between concentration of reactants and the rate of reaction. We usually just call this the rate law. Integrated rate laws, the relationship between concentration of reactants and time. So again, both are concentration of the reactants, rate of the reaction, rate law, time, integrated rate laws. So the rate law of a reaction is this math relationship between rate of reaction and the concentrations, as well as these homogeneous catalysts as well. Those will just be incorporated. Rate law must be determined experimentally. There's no way you can just look at something without doing experiments in order to determine that. Now, when we're going to be looking at it, these have already been done, and we're going to use a lot of the data provided. So the rate of the reaction is directly proportional to the concentration raised to a power, as you'll get to see. So rate of a reaction, let's say you have a generic equation. The rate law would be given as K is a constant. It is temperature dependent. Now, it doesn't say higher temperature means a bigger K or a smaller K. Just think of it as a different K. Orders of the reactants, these are the bond orders. I'm sorry, not bond orders. These are the orders of the reactants. So you can see that N and M are not matching the coefficients. They don't just match the coefficients. You need to do more of that. So rate laws, this has the exponent on each reactant of the rate law is the order with respect to that reactant. Sometimes you might be saying, what's the order of hydrogen in the next example? That would be what the exponent is of that. The order of the whole reaction is the sum of the exponents. So there's the order with respect to the reactant. Order of the reaction is all of them added up. Now, single-step reactions really don't match unless the reaction happens in one single step. And that this whole unit is to show that doesn't occur. So it's not going to happen generally in one reaction. However, we will use this with what's called elementary steps. And these elementary steps will kind of look like one-step reactions, but they're really just the parts. This really is not very common. So I'd kind of have you disregard that something happens in one single step. So, although I will show one that does occur, this one does occur in a single step, but this actually will be kind of a forecast of what we'll talk about as elementary steps. So let's say this did happen in one single step. It would really have to say so. But we could see that the coefficient of the chemical species that we're talking about becomes the exponent. And 1 becomes this. So the order of nitrogen monoxide is 2. Oxygen is 1. The whole thing is third order overall. Now, these orders will have a key role in talking about what will a graph look like when these things are plotted and trying to determine what is the order of any chemical equation. K is often left out. It's a constant. It's generally not looked at except for things like unit to make our rate overall correct. So there's a couple methods that we'll go through. Method of initial rates. Now, we often don't know if things will happen in 1, 2, maybe even 3 steps. So we have to recognize these things by patterns to figure out what each order with respect to each chemical species is occurring. So we systematically change the starting concentrations of various reactants while holding the other ones the same. So the idea is that we're constantly, we only have one thing constant, the other thing variable, and by that we can determine what the order of that particular changed species will be. We see how the rate changes as you change the concentration, and what the relationship between the rate and the concentration, that tells you the exponents. So let's see one in this idea here. So writing a differential rate law, write the rate law, determine the value of the rate constant and the overall order for the reaction. So we have a given equation. We can see that we have changed concentrations. It looks like we've done it a few times. And we have these here. So we can see that we kept chlorine constant, changed the concentrations. We could also say we kept these constant and changed the concentrations, each giving us different rates overall. So we're going to use the method of initial rates. So we first want to look at one concentration here. So when nitrogen monoxide doubled, we can see that the concentration, the rate quadruples. So when this rate quadruples, when we double the concentration, that means the rate is second order with respect. So when we think about the order, it's always about the thing that we're not holding constant. So let me repeat that again. I can see when I doubled the concentration, the rate quadrupled. That means that would be second order. Now I'm going to do the exact same thing, only now with chlorine. I'm going to keep nitrogen monoxide constant. When I double the chlorine, I see that it doubles. That means that that will be first order with respect to chlorine. If I remember right, when the rate is the same, that would be zero order. And we'll rarely ever come across third order. So really 2, 1, and 0 are going to be our main hits, except when we talk about a thing called half-life. So part 2, determine the rate constant, including units. You can use any of the trials, it doesn't matter which one, because now that we know the order, we can plug in the values like we do here, this being squared, this being times 1, and we have our rate at that moment. Multiply all these together, our units cancel out, leaving us with our K going to be liters squared over moles squared times seconds. Now, keep in mind your rate is always going to be moles per liter seconds. That's the whole concept, because it's molarity times seconds. That's our rate. So the idea here is that, well, I should say per seconds, I'm sorry, because this would be molarity per second. So the idea here is we need to have units that are going to cancel out with what we already have in order to get our final units. So this is what I was just speaking of when I talked about units. So you know it's going to be molarity per second, always. So if the idea is this is molarities per second and I've got K, this is molarity squared times molarity. Essentially when I divide both sides, I have the molarity cancel out and I have 1 over seconds times molarity squared. This could also be broken up in the ideas of mole squared over liter squared. Makes it a little more complicated. Other ways you can represent it just becomes a little bit more complex. All of those would be good. I like this one the best because it's going to easily cancel out and leave me in molarity per second. So writing a differential rate law to determine the overall order, that's the sum of the exponents. So this one's got 2, this one's got 1, total of 3. So the reaction is third order. So when we're looking at just the effective orders on rate, like I talked about before, I was a little unsure, but here they are. If you have a 0 order, there will be no change on the rate. That doesn't mean you just exclude it, it's just to the 0 order. When you have, or I should say you do exclude it, it doesn't have a role because something to the 0 power is 1. So therefore, changing the concentration has no change on the reaction rate. Order of 1 will be twice as much. Order of 2 will be 4 times as much. Like I said, less common 3 will be 9 times as much. Generally, there's not a 1.5 or a -1. They're just not looking for that kind of thing. Not as common that we're going to see across our AP levels. All right. Be sure to come in with any kind of questions and hope to catch you on the flip side. Take care.